Hi, I'm Tadek Kilian, and so this is work that was mostly done by Zeyu and Bonan at Edinburgh. So they did most of the work, and I'm just here to present because they could not make it to Edinburgh. So they could not make it to Toronto to present their work. So I'd like you to imagine that you are an alien scientist visiting Earth for the first time. And so you observe that on Earth, people have this tradition to put this substance called honey into this other substance called tea. And whenever they do it, what happens is that tea gets sweeter. Right? And so as a scientist, you extrapolate from this observation, and you declare that whenever any other liquid is put into tea, then tea becomes sweeter. And of course, we realize that this is not the correct answer. And we know that the correct answer is that honey tends to make things sweeter. But what makes this sort of generalization problem very difficult is that, I guess from a purely logical point of view, there is no real logical reason to think that one of the answers is better than the other, like given only the observation that you had. And so I guess the standard answer for why we are able to generalize, despite the fact that generalization is a very hard problem, is that we have inductive biases. And so recent work in the lab suggests that we use causal roles as an inductive bias when we have to solve those kinds of generalization problems. And in particular, people have the tendency to parse events as involving a causal agent and a causal recipient. Right? So the idea here is that the honey is the causal agent, and the tea is just a recipient. And then we have this idea that really we are investigating the causal power that resides in the causal agent, here honey. Right? So in other words, the causal law is centered around the causal agent. And so this is why we are able to generalize the predictions that we make when the new observation involves the causal agent again. So here we predict that honey will make milk sweeter because the causal agent is the same. But we will not predict that another causal agent, like milk, will make tea sweeter. Right? So I guess another way to phrase this is to say that we are trying to infer local causal laws, and that sometimes we think that two events involve the operation of the same causal law when the causal agent is the same. But when only the recipient is the same, we think that different causal laws are operating. Right? And so I guess that here I have been using an example that involves already like real-world knowledge, but we can study the hypothesis in the lab by asking participants to observe new objects that they have not seen before. So for example, you might be asked to observe this interaction between those two new objects, those two shapes. Right, so what you observe is that this is what happens before, and after the interaction, the object on the right has changed shape and has changed color. And so your goal is to infer what is going on here, like what is the causal laws that determine what happens in that kind of information. And so after we have given you a few events like this to observe, we then ask you to predict what will happen in other situations where maybe one or two of the objects have been replaced. And our hypothesis is that people kind of spontaneously think that the object on the left is the causal agent, right? It is the square that does something to the triangle in virtue of something that's inside the square, so to speak. And so we have two conditions in our experiments. In the first conditions, so people are asked to observe several events, and what we do is that the object on the left is always the same. Right? It's always a square. If our account is correct, then it should be the case that people think that all those events provide evidence for the same causal law. Every event that we observe gives us one more data point for what is going on with the square. Right? By contrast, we also have a condition where the object on the left is different every time. And so again, if our account is correct, then we should, participants should interpret every event as giving evidence for different causal laws. So the first event tells us something about the causal power of the light triangles. The third event gives us some evidence about the causal power of pentagons, etc., etc. So yeah, we get one causal law for each interaction. And so this one hypothesis that follows from that is that in the first condition, because people infer a single causal law, it means that they have a lot of data to infer the content of this causal law, right? And so the participants in our experiments should all more or less converge to the same hypothesis about what the causal law is. So we should observe high agreement between participants for what is going on with this law. By contrast, if people are actually inferring one causal law for each interaction, then it means that every event that they observe provides us with a single data point for what is going on with the power of a light triangle. So if participants really think that they have only very little data per causal law, they should be very uncertain, and this makes the prediction that there should be very low agreement between our participants, right? So far what I have done is to make a verbal version of our argument, but what I have just said is really just a simplified version of a prediction that falls out from a more sophisticated computational model of the way people solve those kinds of causal-based generalization tasks. And we can go back to the model in the Q&A if people are interested. And I should say you should also look at the paper that came out last year in which people, Bonan and her colleagues, describe the model and show that it accounts very well for how people actually solve those tasks. So to reiterate, our method involves a learning task where people observe 6 observation trials. In the first condition, the object on the left is always the same, whereas in the other condition, it is the object on the right that is always the same. And so we hypothesize that people will kind of parse the event as involving the fact that the object on the left is kind of a causal agent and the object on the right is a recipient. And then after they have observed those 6 trials, they are asked to make generalizations. So for example, you are shown this new situation with 2 objects, and you are asked, what do you think will happen to the object on the right after the interaction? And so again, we predict that in one of the conditions, people will agree with each other more. And we compute the extent to which participants agree with each other using Cronbach's alpha. What we find is that in accordance to our prediction, in the condition where it is the object on the left that remains fixed, that is the causal agent is always the same across situations, people tend to agree much more with each other than in the situations in which it is the object on the right that is always the same. And so this replicates past work on using the same experimental paradigm. So we take this to show that people do engage in some sort of causal parsing of the event in terms of an agent and a recipient, and that they use this as an inductive bias to guide their generalization. But this result kind of raises this broad question of why is it that people actually engage in this causal parsing of the event? So why is it that they think that one object is the causal agent and the other object is the recipient? And so we run 3 other experiments to try to get at this. Like, what are the cues of causal agenthood in this paradigm? And we identify 3 possible cues in the original experiment. So first, the left object moves in our animation, whereas the object on the right is always static. And so this might be something that cues people into the fact that the object on the left is the causal agent. Also, the left object is highlighted. There is a causal, a yellow border around it, so it might kind of make it more salient. Also, it is the right object that changes state after the interaction, whereas the object on the left always remains the same. And so it might be that each of these features independently contributes to this kind of perception of causal agenthood. So what we did is that in addition to the original version of the experiment that I have just shown, we specifically removed each cue from the setting in order to see whether it would have an effect or not on the causal asymmetry. So we had an experiment where we kind of inverse the direction of the movement. Now it is the object on the right who goes into contact with the object on the left. We had an experiment where the stability is different. That is, the recipient stays the same after the interaction, but it is the object on the left that changes features. And finally, we had a version where we removed the yellow border around the object. So this is just a reminder of the design of the original experiment, right? We have people who have the object on the left always the same, people who have the object on the right always the same. And so we kind of do the same thing for all the three new experiments that I have just described. So these are the results that I have already shown you. So this is just a reminder that in the original setup you get a causal asymmetry which replicates past work on using this paradigm. Now we ask, will we still observe this causal asymmetry when we remove any of those original cues? So when we remove the movement cues, we find that here people agree with each other to the same extent regardless of condition. So there is no more causal asymmetry. And we find the same results if we remove the stability cue, as well as when we remove the yellow border. So this suggests that the causal parsing of the event is quite fragile. Any cue, when it is not present, kind of removes the asymmetry. Right. So to sum up, we replicate an effect that was first found in a paper from our lab from last year, which suggests that there is a causal asymmetry in inductive generalization. And so we take that as indicating that people tend to parse an event into a causal agent and a causal recipient, and that in turn acts as an inductive bias that guides the way that they make generalizations. We also find that this causal parsing of the event is quite fragile, because it depended on every of the cues that we had on the original setting. So we think that those are quite exciting findings, and they open the way to very promising future lines of research. We do want to emphasize that this is still preliminary data, right? And so we should maybe replicate this experiment with larger samples. We might also want to investigate other cues, right? We find that it is interesting that even with this kind of artificial kinds of cues, people are induced to parse the event in this particular way. It might be interesting to see what happens in another setting when we use different cues. We have also investigated the causal asymmetry effect by looking at the extent to which people agree with each other when they make generalizations. And it might be we had very good reasons to do so, because this is a prediction that falls out in a very natural way from a computational model. But there might be many other dependent measures that could be used to get at the same general idea, right? So now maybe I want to take a step back towards the big picture. The term causal asymmetry has been used in the literature to describe a whole host of phenomena, one of which is the fact that if you look at this classic Michotte display, you will probably describe what is going on here by saying that the left ball caused the right ball to move. And it seems like a very natural way to describe the event, but you could also say that the right ball caused the left ball to stop. And people have been pointing at the fact that, from a purely objective, Newtonian mechanics view of the world, those two statements are perfectly equivalent. There is no reason to think that one of them is a better physical description of what is happening than the second one. And so this has motivated this sort of idea that, well, the human concept of causation is a very naive one. And we think that there might be more to the story. And so it might be that the fact that we parse events into causal roles, like there is a causal agent and there is a recipient, even though it does not reflect a purely objective scientific state of the world, it might actually act as a very powerful inductive bias that helps us make better generalization. And I guess this is consistent with this idea which has been gaining traction recently in the causal cognition literature, which is that the causal representations that we built are not necessarily designed to be as objectively correct as possible, but they are designed in order to give us the most inductive potential that we can. And our results might be one little data point in favor of this. Okay, I'd like to finish by thanking my collaborators, in particular Zhao and Bonan, who again did most of the work, and our supervisor, Chris Lucas. Okay, and thank you for your attention. I'm looking forward to your questions.
Thanks. That was really, really great. I wanted to ask about, so the one thing that sort of didn't seem to come up in any of your experiments in terms of affecting causal asymmetry judgments, but that seems really relevant, was time. And I get that it's very hard to divorce any of these other things, like which one is moving or what comes from the left or the right, or which changes it doesn't, from time. It's very hard to isolate time because it's all happening in time. But it does seem like we do typically infer causal asymmetry temporally, and I think there's a lot of people coming out of physics and things like that that would say that the causal asymmetry is ultimately going to be derived from the arrow of time. And then what you think about that is ultimately a question of, what do you think about the arrow of time? If you think that's objective, then you're going to think these causal asymmetries are objective. If you think that we're in the blocked universe and we just sort of project an arrow of time onto the world because of thermodynamics or something else, then the same would hold for causal asymmetry. So I guess it's just an invitation to kind of say some things about where you think time fits in with all of these results and with this sort of broader idea of causal asymmetry as a kind of potentially fruitful inductive bias.
Thank you. Yeah, I think it's a great question. And there's probably a lot of research left to be done on how time induces the way that we frame events. Maybe I'd like to remark that in the kind of classic display, the first ball starts moving, and so we kind of see it in motion before the other one. And so it might be that one of the reasons we frame the event in this particular way is because of this temporal asymmetry that is there. And so yeah, even if from the purely scientific Newtonian mechanics kind of story, the two different controls are equivalent. This temporal asymmetry that is baked in might induce us to say that, well, no, it is actually the first ball that caused the second ball to move. And I don't know if it is a completely rational thing to do in that particular case, but it might be that using time in this way is in general a very good inductive bias. Yeah, thank you.
Hi, thanks for your talk. Very interesting stuff. I was just curious, as you state there on the slide, parsing events into causal roles might provide a useful inductive bias for subsequent generalization, and I agree that it might do so, but do you have any idea why, or an explanation of what characterizes agents and recipients that allows for this generalization?
Yes, great question. Well, I think that in general, in the world, it is the case that causal laws tend to cluster around a particular thing. So it is actually the case that honey has some sort of causal power, there is sugar in it, and that's why honey tends to make things sweeter. And it's not that anything you put into tea will make tea sweeter. And so my guess is that we like causal cognition is kind of designed to look for that kind of things. Now, I think an interesting question is like, how do we actually identify those? So here, like in the stimuli that we have employed, like I don't think there is like a right or wrong answer for like which cues you should look for, or maybe there is, but yeah, we didn't really have a very strong like normative argument for why it should be the case that movement should be a guide to causal agent status. We were mostly inspired by the fact that, well, there have been results on the causal asymmetries that comes from studies on causal perception that indicate that like this is very strong cue. But there is probably a lot of work that remains to be done for why those should be valid cues that actually work as inductive biases. All right, we're out of time. I'd like to thank you again for listening to me. And our next speaker is Kevin O'Neill, who will be talking about measuring and modeling confidence in human causal judgment.